Okay, now that we've got everybody in, we've got 2 more talks for you. We've kept the best for the end. Just kidding. I'm kidding. We've kept the best for the end. And it's a great pleasure to welcome Anima Anandkumar from CalTech and NVIDIA to tell us about bringing physics into machine learning. Thank you so much for coming.
Thanks a lot. Thanks a lot, Ali and George and Pablo and Ben for organizing this event. It's so timely, and for Ben live tweeting it, it's trending on Twitter. So there is a lot of interest, and I was, in yesterday's discussion, I guess this came out on how we can grow this community and really realize the impact from so many disparate areas, right? So I started my career in EE in signal processing and information theory, which are sister areas to control. And so seeing kind of coming back to that has been a full circle for me. Collaborating with many control theorists and systems people at CalTech now, is an exciting new venture for me, and I'll show you some of those results and ask, there is the side from the control theory perspective of how to infuse learning, and then there is the learning perspective of how to infuse model-based control or physics and structure, right? So both those perspectives, need to come together. So in control theory, we mostly think about stability guarantees, whereas in learning theory, we think about generalization guarantees, right? Like, how do the two come together? I feel like the foundations still need to be completely resolved, but we are taking some first steps in bringing them together, right? So can we have now a framework where we guarantee stability? We also look at generalization, and what would be the learning frameworks that can guarantee both. And so that's an overview. And that's kind of like the perspective, right? So from the learning perspective, the idea is not to go with purely data-driven approaches, but also to use priors. And the priors can come in many different forms. In the context of control systems, a lot of it could be like physical laws or models of existing control systems, existing controllers that we can use and then build on top of that with the use of additional data. Or it can come from structures like tensors and graphs. For those who know my past research, a lot of it has been on incorporating these higher order tensors and looking at how we can go beyond matrices and what are the gains we can realize from that. So you can now build those structures into algorithms and into neural network architectures and hope for better gains than a standard neural network, right? There could be other forms of domain knowledge that can be useful. I won't talk about it here, but we've done works that combine symbolic knowledge or symbolic expressions along with data, right? So input-output data of functions as well as symbolic expressions that relate different functions. How do you build embeddings that incorporate both this knowledge together? And then lastly, simulations or synthetic data. If we cannot have all the data in the real world, how do we do it with synthetic data? And here you saw so many talks that looked at simulating robots, right, or robotic arm and different tasks in simulation. And then there is the challenge of sim to real, how to bring that to the real world. So that's how I classify when I think about what prior knowledge do we bring into learning. And I think this is the right time to be thinking about it because, in my view, many of the low-hanging fruits of plain black box deep learning are getting mostly exhausted, at least in domains like where there has been a lot of activity, right? So the question of what additional structure to impose, what is the right amount of prior to impose, and what's the right amount of data to obtain depends. It's very application dependent, but we need to think of it, right? We can't do this purely black box data-driven approach of taking a standard neural network and hoping things will work out. And so I would say that would be the main takeaway from this talk. So let's now look at some examples of how we can incorporate priors. And as I said, the main focus will be on control systems. So I'll start, and this work is done under this new center we have at CalTech called CAST, or Center for Autonomous Systems and Technologies. And the idea is to do an interdisciplinary, have an interdisciplinary group of people who can really bring expertise and ideas from different perspectives. And in this first project, which appeared in ICRA just a few weeks ago, like how do we ensure stable landing of drones while using learning, right? Like can we use learning to learn the dynamics better and improve the landing of drones? And there are many talks here in this workshop that are very related, right? Like how to build learning into control systems. And so if I guess this is the familiar model-based control where we have the evolution of the state, and we assume there is this nominal model that will predict what the next state should be, but then there'll be unmodeled disturbances. By the way, I'm using a hybrid notation, so I have S but U. So I like to think of myself as a bridge and as a person who likes to be in multiple areas. And unconsciously, I did this hybrid notation. So yeah, so that's the idea, right? Like you hope that this model is a good model, so you can have a small amount of error, and then you can quickly stabilize and converge to the steady state. But if the model is wrong, then these errors will be large. And even if you can guarantee stability, it could take a longer period of time for this system to stabilize. And so this is where we can have right? So that's the idea of robust control is, for any arbitrary perturbation within a bound, can I ensure that there will be still convergence, right? So this is the standard Lyapunov analysis, and we can, we have everything that's well defined here. So, but then if we go to the learning-based system, we can now utilize, let's say, a neural network or similar model to approximate and predict what will be this unmodeled disturbance. So the residual from the nominal model, let's try to learn that by using a learning framework. And so now we can augment our state estimation, right? And then we hope that this error gets smaller. So we can now hope to converge faster than before. But then we still want to maintain stability, right? So the idea is if we now introduce an arbitrary neural network, it's no longer stable, right? So, so by itself, you won't have stability. But on the other hand, if we have a bounded Lipschitz constant, if we ensure that the input to output map here has bounded perturbations, then we can ensure stability. So, and we'll see later on, this is actually quite crucial. When we just put a standard neural network with no normalization, right, no bounded Lipschitz constant, it actually crashed the drone. So it's important to think about, not just from the theoretical perspective, it has an impact on practice on how we design learning into these systems. So that's the idea of incorporating learning. And in the case of drone, why is this important, right? So these are the dynamics equations, the control equations. And the main aspect here is, when especially the drone is landing and closer to the ground, it's very hard to model these aerodynamic forces. How the rotor and the wing foil interacts with the ground is hard to model, and that is the part that we can't easily write down, right? The other aspects, it's from the Newton's laws of physics, or it's like there's the thrust coefficients and other aspects that we can measure, like Sunjo and Guanya and his students did these bench tests and like measured, aspects. And so essentially, if you abstract all that out, there are parts that we don't know, right? This Fa is the unmodeled force, and this tau A is the unmodeled torque. And so other than that, everything else we know. And so you can think of this from the learning perspective as there is known physics. Like I know, all aspects of the model except this unmodeled force and this unmodeled torque. And for now, we will leave out the unmodeled torque because when it's close to the ground and there's no wind disturbance, external wind disturbance, right, that's not the crucial one. I know the angular part is not, there isn't going to be a large part of external torque, right? Whereas we do have the external force, which is the ground effect, and that's what we would like to estimate. And so that's what we'll take away from this slide is there is this additive residual force that we need to estimate. And now how do we use the neural network and collect data to learn a better ground effect model than some of the parametric models that are available in the literature. And then once we have it, we can then use that to correct our controller, right? So we use the simple nonlinear feedback linearization. So we are, if there is the nominal controller that's just using the, the nominal model where this FA, this external force is just set to 0, right? You don't know what that is. So you model everything else, and based on that, you can come up with the controller, with the control signal. But then we can now incorporate the additional residual as well, and then change our control signal, right? So this is standard. We can now take from our state estimation to changing our control signal, and it'll also be additive. So because of the linearity. And so this is the standard setup for now incorporating learning and correcting our controller. And we'll see this later. I mean, in order to ensure robust control and stability, we'll have to ensure that there is bounded Lipschitz constant, and there is small time delay. So there's also smooth trajectory. So these are all standard assumptions that's made to ensure stability. So the aspect is, of course, it all starts with data, right? So, and in this case, we went out and collected data. So the data is both the state and the control signal, and then the output would be this external force. We have this motion capture at CAST, and there were also these reflective infrared sensors. We outfitted the drones. And with that, we had the expert fly the drone at different heights, different kind of trajectories. And then from that, we have the data collection. So we can now measure the ground truth external force. So we have the input-output, right? So we have the label data to input to our neural network. And as I said, we used a simple multi-layer neural network, but then we spectrally normalized it to ensure that it will be stable. And you can see that it can get a pretty good estimation of the ground truth, right? So naturally, this the appropriate neural network would be able to fit this data. And so the question of how big that neural network, that's the hyperparameter you tune, and then we can fit this well. And I guess the only important aspect here to notice, the other parametric models that's been used in literature are very poor. Like they have a poor fitting to this ground effect data. And that's because these aerodynamics are extremely complex to model, and people use some very simple models. They assume only the z-axis matters for the ground effect, which is not true. If you're landing in an angular fashion, you will have other effects. And it also changes from drone to drone, right? And it's, so it's very hard to model. And that's where a black box neural network is perfect, right? If we have trouble modeling, that's the appropriate place for using this neural network. And so, I guess first, ensuring that it fits well on the training data is a good start. The next question is how well does it generalize, and how, of course, does it make the drone fly better, right? So that's the next natural questions. And what we see is that spectral regularization here matters a lot. So if we just use this fully connected ReLU network, right, I think 4-layer network, so from training to test, you can see big changes, right? So here, we are asking for more. We are testing at much higher velocities of landing than what we are trained on. So there is domain shifts here. And in this case, it's a challenging question to generalize, and we don't see it in a standard neural network. But spectral normalization does a much better job. It's much more graceful change of the signal, right, because it's a bounded Lipschitz constant, so you have much smoother change compared to a standard neural network. And so that makes a difference in generalization. And actually, there's a generalization theory by Peter Bartlett and others that look at bounded Lipschitz constant neural networks, right? So it's also important to give generalization, to prove generalization bound, spectral normalization is also required in these frameworks. So it's interesting, it's the same requirements that matter both for stability and generalization. At least they are very tightly related, which I think is interesting. And this is the result. This is kind of showing the stability bound, right? So if you had no error in estimating this ground effect model, of course, you will converge to the right solution. Otherwise, there will be some residual error. But the key is that error depends on the Lipschitz constant of the neural network. So naturally, you expect that it's a bounded Lipschitz constant to ensure there is stability in the overall network. So it appears both here and here. So it's and then there are other, of course, aspects like the control gain that also determine stability. Right, so the idea is we can still provide stability guarantees even when we add learning in the loop. And so this is the result. So the neural lander is the one on the left. The baseline is on the right, where there's no learning involved. And so notice the landing. So you can see that it landed smoothly and gracefully, whereas the baseline was still hovering a lot. I guess it's made to loop again and again. But the idea is we can see that in many tests, and we have a lot of quantitative results in the paper, that there is significant improvement in the speed and smoothness of landing, right? But at the same time, it's still stable. It doesn't crash. So that's a good aspect. And also high precision movements. In this video, you can see the drone being extremely close to the ground and being able to do these maneuvers. I think Guanya has other videos on tabletop and doing all these different movements. So all kinds of high precision movements by using this really good ground effect learned model, we can enable that well. So as the next step to this project, we've been thinking about how to automate that data collection part, right? So right now, manually, there was an expert flying the drone, and we collected the data, and we could learn this ground effect model. But then the hope is we can do it automatically, but still have safe exploration. Like yesterday, Andreas Cross talked about safe exploration, right? Kind of trying to explore whether we can take to go at a faster speed of landing, but still be within the uncertainty bounds, ensuring that we can still safely land. And it's natural to think about it because we can try to do land smoothly, or we can go for a much aggressive one, right? But with that, you don't want it to crash or destroy the drone. So how do we do this? So I won't go into a lot of details here. This is still work that is under development. But the idea is we can use notions of robust regression to be very conservative in ensuring safety. And so what robust regression is able to do is handle the covariate shift. So I talked about the domain shift because each time you're trying to land faster, right? So it's going to be a different distribution from which you've learned the model of the ground effect. In this one, we can ask, given that there is this covariate shift, what is the min-max estimator? Right? So by doing the min-max approach, we are being conservative about our uncertainty. And hence, we can ensure safety and generalization under this framework and do this now iteratively. So we'll progressively try to land faster and faster, but still maintain safety bounds. And in this plot here, you can see that there is like the ground truth, right? So this was using the data we had collected from the drone. Now we simulated it and asked if this is the ground truth value of the ground effect force, can we estimate it iteratively using the deep robust regression model? And you can see that there is now the velocity you're progressively increasing, but you're always doing it within the uncertainty bound, right? You're not going beyond. So you can see, like in 10 iterations, it's able to get like a much better estimate of like the heat map. This is the ground truth. So ultimately, this is what you want to learn. But in the beginning, you don't know, right? You don't know how the ground effect model is at higher velocities. So you're progressively learning that in an automated way. So I think there are a lot of interesting questions here on how we can ensure both safety and stability and generalization. What is that interplay of these quantities? And is spectral normalization the right framework? Are there other learning approaches that can guarantee this? I think that's very much an open question. And so another aspect we are going to test, we've started thinking about is like external wind conditions. So far, I said this external torque is something we ignored in our estimation, but we will have to do that once we have data of wind conditions. So this is a unique wind testing facility that's available at CalTech. It's about 1,200 programmable fans. So you can program these fans and create all kinds of interesting wind conditions. And we can certify like how much the drone would be safe under different kinds, speeds of wind and different trajectories of wind, right? So I think we are very excited to ask, what are the limits of learning in these kind of systems? And as you can imagine, there are big domain shift problems here because you could have a whole range of wind conditions, and the new wind condition is something you're unobserved. So it's part of it also is meta-learning because you want to learn the model not just for one wind condition, but multiple wind conditions. But at test time, you don't know what the wind condition will be. So from the learning perspective, I think these are very challenging problems. Yeah, so the takeaway from this I want to kind of emphasize is, right, so the control methods have been analytic methods. In model-based control, we assume these Newton's laws of motion. Based on that, we design our controller. And then, but with learning, we are able to improve the precision and improve the efficiency of landing, but still keep stability, right? So we are, from both control perspective and learning perspective, we are ensuring it's stable and generalized as well. And so that's what I think this interplay makes it very interesting. Since I'm mostly out of time, I will skip some other aspects I wanted to talk about. So some of my previous work was on tensors and even ongoing work, but so one aspect is thinking about neural network architectures that can incorporate these higher order tensors as a way to better model higher order correlations and come up with better estimates in challenging tasks. For instance, one of them is long-term forecasting, and we see much better ability to forecast into the future with these models. And so, if you're interested in using tensor methods, so TensorLi is this open source frameworks that makes it very easy to use tensor operations and build them into neural network architectures. So I encourage you to go try it out. I always make sure that I have a slide on this to encourage people to use it. But lastly, I think one aspect that's very challenging in these systems is data, right? We will never have enough data to really truly model these systems. And and also there will be domain adaptation and shifts in our learning that we need to incorporate. So I talked about incorporating pre-existing structures such as physics as a way to overcome this, but there's a whole plethora of other approaches. Active learning, semi-supervised learning, of course, and simulations. And I just want to quickly have a word about Isaac Sim and Isaac SDK, which is the platform for robotics launched by NVIDIA that looks at being able to simulate navigation, grasping, and other robotic tasks, and then take that onto real robots using the Jetson and the Xavier platform. So I encourage you to go check it out. The other one that I'm very excited about is the NVIDIA Drive simulations and the Drive platform, right? Like how much of like this autonomous driving here, we saw many talks, what can we do in simulations effectively before taking that to the real world, how we can simulate accidents and other kind of risky behavior in these frameworks at scale will be very interesting to do in future. So yeah, so thank you, and out of time, so I'll stop here and take some questions.
Thank you very much. Thank you, Anima, for a wonderful talk. We have time for a few questions. One there.
Hi, quick question. I was wondering, in the training phase of the model, how do you measure those external disturbances, those forces?
Yeah, so through this, as I mentioned, in the first work, the expert is like flying the drone, and we've fitted it with sensors, so infrared sensors, and we have the motion capture. So it can capture the velocity, the position, velocity, and all these coordinates.
So that
along with the, and then the external force is measured by the equation I showed, right? Because the equation, there was the thrust coefficient that needed to be measured, but we can do that with the bench test for the drone. So whatever is the residual will be the ground effect.
So that
force.
means that the forces are measured because you know the inertials, right? You know,
right.
You know the velocities and positions and so on, right. So you can back out what the forces would be.
That's right.
So my question is, if it's running in real time when you're actually running the robot, presumably you also have inertial measurements there. Could you not just...
So online learning is extremely challenging, right?
But
we wanted to start with enough offline data collection and learn the model to...
I guess my question then is, it seems like you know the forces just as well during training as you do while the thing is actually running, because you have those same inertial measurements.
Yeah, but also this used motion capture, so you may not have...
Oh, so you have better inertial measurements during the training.
That's right.
I see, okay.
That's right.
Thank you.
Okay, there was another question on this.
Oops, oh my God, I'm sorry. Walk too close to
Yes, too close.
Hey, hi. My question is, how is the model incorporated in generating the landing trajectory? Is it doing some receding horizon control or other methods?
So in the first work, it was just manual like design. We said, let's fly at different heights and let's kind of do circles. So it was just kind of having enough diversity of data.
Oh, sorry, I'm asking about how is the learned model incorporated in generating the landing trajectory?
Yeah, so that was like the residual, right? So this is so in the state estimation, there's this additive residual, and then because it's nonlinear feedback linearizing control, so that'll be the residual control signal.
All right. Yeah, thanks.
Thank you very much, Anima. Thank you.
Yeah, thank you.